Imagine a world where humanity's footsteps extend beyond our own planet, where astronauts soar through the infinite expanse of space, and where the moon, our celestial neighbor, beckons us with its mysterious allure. Join us on an epic voyage as we embark on a bold mission to send astronauts to the moon, discovering new secrets of the universe and pushing the boundaries of human exploration to new heights. The next giant leap for mankind awaits, and you're invited to be part of history in the making. In the early 70s, NASA launched the first man to the moon. Now in these times, NASA aims to launch astronauts to Mars by the late 2030s or early 2040s. Making the vision a reality will be challenging, as the first steps in developing these long-term missions is to practice with Lunar mission to acquire additional knowledge and establish the first long-term presence on the moon. Our team LIDO, short abbreviation for Lunar Explorer and Transportation Offloader, was tasked by NASA RASCL competition, which calls for a lunar surface transporter vehicle that would not only extend astronauts' exploration capabilities but also perform offloading, moving, deploying, and supporting payloads up to the scale of habitats. Is it possible to design a lunar surface transporter vehicle and extend lunar exploration capabilities?
The Lunar Surface Transporter Vehicle prototype was based on a conceptual design as shown by the CAD model. However, several changes were made to improve its functionality. Firstly, the cabin was removed as it was deemed unnecessary to complete the mission. Additionally, the suspension system was changed to 6 shock absorbers and springs to provide better stability on rough terrain. Further, the initial plan for independent steering for each wheel was scrapped, as each wheel is equipped with its own motor. This configuration allows for greater flexibility and ease of control. The vehicle's design was also updated from single-level to 3-level structure. This alteration was made to accommodate the electronic and power sources under the bed and the mechanical arm. As the cabin was no longer present, the weight distribution had to be adjusted for the crane's placement. With the current suspension system, placing the crane at the end of the bed would have concentrated the weight on one side, leading to instability. As a solution, the mechanical arm was shifted to the middle to ensure equal weight distribution. The vehicle has a length of 15 inches, a width of 8 inches, and a height of 9 inches. The height from the top plate to the middle plate, where electronics are housed, is 2.5 inches. The motors used are 1 inch in diameter and 2.25 inches in length, with a torque rating of 5 kg/cm. The motors are insulated to reduce heat and keep the environment out. With this new suspension system, the vehicle can carry a maximum payload of approximately 25 pounds, while the mechanical arm can pick up a payload of up to 4 pounds.
The LSTV is a specialized vehicle designed for transportation of large payloads on the lunar surface. It is equipped with advanced mobility systems including propulsion, navigation, and communication systems. The concept of operations for the LSTV consists of the following elements. Deployment. Once landing on the surface of the moon, the LSTV is deployed from a lunar lander or similar spacecraft. Upon landing, it is ready for operation and its systems are powered up. Next, operations. The LSTV's operations on the lunar surface include traversing the terrain to reach designated locations and carrying out payload handling operations to specific locations such as a lunar base. Finally, mission completion and return. Once the LSTV has completed its mission objectives or has reached the end of its operational life, it may return to the lunar base or designated location, decommissioning, or return to Earth.
For conducting theoretical analysis, we relied on SOLIDWORKS and finite element analysis in ANSYS. While SOLIDWORKS was used to design the model, ANSYS was the go-to option for gathering analytical data about the deformation of our vehicle when loaded on the crane. Together, these powerful tools helped us obtain accurate information about the extent of deformation and optimize our design accordingly.
Now we will be discussing the testing and full mission trial of our prototype. The testing was conducted in several phases. Phase 1, forward and backward movement. Phase 2, turning. We moved on to testing the turning capability of the prototype, including a 180-degree turn. Phase 3, payload testing. We then tested the prototype with a payload, starting with 5 pounds on each side and then increasing to 10 pounds on each side. We tested the prototype's ability to move forward and backward with the payload. Phase 4, mechanical crane testing. Next, we tested the mechanical crane's ability to pick up payloads of various weights. Phase 5, tough terrain testing. We tested the prototype without a payload on tough terrain to see how it would perform. To demonstrate the feasibility of the prototype, we conducted a full mission trial. The trial involved exiting the rocket from an off-ramp and loading the prototype with weighted payloads. We then drove through rough sandy terrain until the prototype reached a suitable base location. At the base's location, the prototype offloaded the payloads. The final segment of the mission was returning to the landing site to retrieve and load additional payloads.
Here is footage of testing with multiple point of views.
In conclusion, the successful development of our lunar vehicle prototype signifies a major milestone for Team Lido. Through meticulous design and comprehensive testing and continuous refinement, the lunar vehicle has demonstrated its ability to operate, transport, and offload payloads, potentially opening the doors for future lunar missions and propelling us closer to realizing our aspirations of sustained human presence and exploration on the moon and beyond.